In this lesson, we're going to discuss how we can go backwards from trigonometric functions. And instead of being given an angle and finding the corresponding function value, we're now going to be given the y value or the function value, and we're going to have to go backwards to find what angle results in that function value. In general, we're used to seeing sine of an angle. Remember that our angle is our input. And when we calculate sine of that angle, we're just saying what ratio do we get when we look at the y value over the r value, or what do we get when we see the opposite side over the hypotenuse. So notice that the output becomes the ratio, and therefore that's our output. But notice that now what we're going to be doing is looking backwards. We're going to be saying that sine inverse of a ratio, sometimes we refer to it by something different as well. Sometimes this is referred to as arc sine. So putting the word arc in front is basically just saying the inverse sine function. So we're now given the ratio. So the input is now the ratio, and the output should be the corresponding angle. And before we finish this one, I'd like you to realize that the answer to an inverse trigonometric function is an angle. And so what we should recognize is that there are numerous angles that give us √2/2 for sine. For instance, I know that pi/4 in the first quadrant will give me √2/2 for a sine value. But even if I'm in the second quadrant, I'm also going to get a positive √2/2. Even if I were to continue for a full rotation, adding 2 pi to each of these, I would get to 9 pi/4, which is just over 8 pi/4, or 2 pi. Or I could get 11 pi/4. Or if I chose to, I could go backwards and realize that if I were to come up with this angle and this angle going backwards, that would give me -5 pi/4, or -7 pi/4. So we've got an issue here because this could give us so many different choices. And at that point, it wouldn't be a function anymore. Because remember, in order for a function or an equation to be a function, one input should yield one output. And in this case right here, we could see that the input was pi/4. I'm sorry, the input was √2/2. The output is supposed to be an angle. So in this particular situation, when I input √2/2, my one and only output should be pi/4. And so how do we know that it's not going to be any of these other remaining angles, even though those give me the same ratio of the square root of 2/2? And this all leads to what these graphs look like, and how, by restricting the range, we can actually come up with all of the possible values for each of these functions. In order to see how the trigonometric functions relate to the inverse trigonometric functions, we're going to start off by reviewing a little bit from algebra on inverse functions. So remember that if I have some function, let's just say y = x³, in order to find the inverse of that function, then our inputs and outputs switch roles. So that means that we're just going to switch the two variables where y was x and x was y. And notice that now this is our new graph. Now in general, these should always be reflected along the line y = x. And so if I were to fold the red graph over the line y = x, I would get the blue graph simply because of the fact that all of the inputs and outputs have flipped roles. So if we take a look at maybe the next function, if I start with y = √x, then that would mean that all of this piece that's above the line is now going to have to be below the line. And anything that's below the line here is now going to have to be above the line. So if I switch the x and y, then this is the graph of my inverse function. Now, both of these functions were special because they were both considered one-to-one functions, which means not only does one input give one output, but every output only comes from one input. And the reason why I'm going to mention that is because now let's look at this one. Let's say we wanted to find the inverse function of this. Well, same way, I would just switch the x and y. And when I switch x and y, notice what we get. Now, even though this is technically the inverse of the graph of y equals x squared, it's not an inverse function because notice it doesn't pass the vertical line test. For one input of 4, I get two outputs of 2 and -2. So if I want to find the inverse function, then what I need to do is restrict the domain. So if I restrict the domain of the parabola to only be x greater than 0, then notice that would imply that the range, or the domain of this new function, where it's now the y coordinates, are going to have to be y greater than 0. And so now, the reason why I did that is that if I didn't restrict the domain, then the inverse would not be a function. And so what I had to do is come up with a domain that would still take all of those y coordinates that I get. Notice that I get all the y coordinates from 0 to 1/2 to 1 to 2, 3, 4, and so on. So when I get those y values, I can just cut off this whole left piece and still get all of those y values. So what I do instead is I restrict the range of the new function to only be y greater than 0. So why don't we go ahead and now look at how this looks for trigonometric functions. Let's look at y equals sine x. So there's y equals sine x, but let's say that we graphed x equals sine y. Notice that x equals sine y is the same function, except now it's riding along the y-axis instead of the x-axis. And the problem is this isn't a function. So what we're going to do is we're going to zoom way in on this. We're going to take a look at all of the values that we could possibly get for sine of x, all the outputs that we're able to get. Now we're able to get a value of 1. We're able to get a value of -1, and 1, and -1, and so on. And so it looks like my domain, or my range for y equals sine x, bounces between -1 and 1. So that must mean that maybe we should restrict the range on this inverse function to only be the locations where the y value is between -1 and 1. Okay. And when we do so, notice that it only gave us one piece of this graph. It gave us the piece of the graph that went from this location over here with a y value of -1 over to this location up here, which is y equals +1. So it actually cut off an entire piece of our graph. And now notice how the domain is somewhere about right here to right here. Now, I actually misspoke a little bit here, because now that I've switched these two x and y values, I don't want the y values to go from -1 to 1 anymore. What I'm basically saying is that I want my original y values to only go from -1 to 1. So if I switch those y values, then I want the x coordinates to go from -1 to 1. But notice there's an issue, because if I just put in x equals -1 to 1, then I still get that original graph that's bouncing back and forth and therefore not a function. So what we do instead is we actually try to find out where exactly does the y coordinate equal -1 and 1. So let's take a look at where that happens. This one right here is at -π/2. This is at -3π/2. This is at π/2. If I continue to scroll over, this would be at 3π/2. So there's lots of locations where the graph is equal to -1 and 1. So what we're going to do instead is we're going to make my new y coordinates, the quantities that I flipped, from -π/2 to π/2. And if I do that, notice what ends up happening to the graph. Notice that now the domain is from, let's zoom in a little bit here. where the old range used to be from -1 to 1, now the new, or where the old range used to be -1 to 1, now the new domain is from -1 to 1. And when the domain used to be from -π/2 all the way up to the maximum of π/2, now I see that the range is from -π/2, or -1.57, all the way up to π/2, which is 1.57. Which is why we don't really want to write it in terms of x equals sine y. What we would rather do is just say if y is equal to sine x, its inverse function is y equals sine inverse of x. Okay, and in doing that, what we're going to basically be able to do at this point is find and go backwards to find what angles gave me certain ratios. If we look at this from a perspective of labeling our axes in terms of pi, we can see that the lowest that sine x ever goes is -1, and that occurs at -π/2. And the highest it goes, traveling through all of those values, those y values, it goes to π/2, which is why the range that we're going to get for sine inverse of x will go from -π/2 to π/2. So why don't we take a look at tangent x now? Now tangent x has numerous pieces separated by asymptotes. But notice that if we were to graph the inverse function, then we restrict that range to only be one of those pieces, which in fact means that we are going to restrict the tangent x function to only be from -π/2 to π/2. Pi/2 is less than x, which is less than π/2. Because if we now do that, the inverse function is only going to be giving y values between -π/2 and π/2, which means that our answers for any tan inverse function can only be angles between -π/2 and π/2, just like sine of x. And lastly, if we were to take a look at another function, let's look at cosecant of x. Notice that when we look at cosecant of x, it also has all kinds of asymptotes at -π, at 0, and so on. But if we're trying to find the smallest interval that includes all of the possible y values, notice that the y values are everything from -1 down to infinity, and from +1 up to infinity. So if we restrict that range to only be the y values between -π/2 and π/2, then notice that we get every single possible y coordinate just by looking at this piece of the graph. Which means when I graph y equals cosecant inverse, the x values that used to be -π/2 to π/2 will now be from -π/2 backwards, x coordinates, and from π/2 forwards, the y, or from -π/2 at the bottom up to π/2 at the top. And notice as well that this value down here is at -1. So if we were to look at the graph here, we can still see that it folds along the line y equals x. And so sine, tangent, and cosecant are all going to be restricted from -π/2 to π/2. So if we go back to our original example, the reason why we had to give the output of π/4 when I was calculating sine inverse of √2/2 and not any of these other angles is because that's the only answer that lies in the interval from -π/2 to π/2. So that's why for sine inverse of x, tangent inverse of x, and cosecant inverse of x, our range or our output y values should always be in this range. So if we now go back to our graph for cosine of x, notice that if I picked from -π/2 to π/2, then I would only get this top piece of the graph. For picking all of these values between -π/2 and π/2, I would never get any of the possible negative outputs. So the smallest interval that we can get in order to make sure that we get all possible inputs, or outputs rather, would be from the top at +1 down to the bottom at -1. And so it looks like we should restrict our range then, or our domain, to only be from 0 to pi, so that when we look at the graph of cosine inverse, notice that my domain, or my range rather, is only going from 0 to pi. Remember, domain is the x coordinates, and I even keep mixing these up as I'm speaking. But I want to make sure that the domain for cosine is from 0 to pi, so I only want to graph from 0 to pi. Okay. Which means that when I fold that over the line y equals x, I'm only going to get outputs from 0 to pi as well. So let's take a look at secant of x then and see why that's true as well. If I look at secant of x and I only looked from -pi/2 to pi/2, notice that I would only get the positive y values if I chose the interval from -pi/2 to pi/2. But what if we chose the same interval that we chose for cosine x, which was from 0 to pi? If I do that, now notice that I get all of the positive y values and all of the negative y values. Now notice I can't plug in pi/2, so that means that I can never get an answer of pi/2 when I go backwards for secant and I try to find the angle. But I do know that all the answers that I need to give need to be somewhere between 0 and pi, which means that when I graph my secant inverse function, then this is what the graph would look like here. And you could see here that the domain is now from everything before -1 and everything past 1, while the range is everything from 0 up to pi. And lastly, if we take a look at cotangent x will be something similar. Notice that all of these intervals are always going from 0 to pi. Each of the asymptotes are between 0 and pi. So if I only restrict to one piece of this from 0 to pi, then that's why my cotangent inverse function will also give me outputs from 0 to pi. We actually have two different ranges depending on what inverse trigonometric function we're calculating. So for the intervals for our outputs to be from 0 to pi, we're only going to get those values for cosine, secant, and cotangent. So if we take a look at what that means, -pi/2 is down here, and pi/2 is up here. So that means the answers that I get need to be somewhere between -pi/2 and pi/2. Or in other words, from 0 looking downwards to pi/2, or from 0 looking upwards to pi/2. But if we look at the range for cosine inverse, secant inverse, and cotangent inverse, now we realize that it's any values between 0 and pi. And so I'm going to be any value, or I'm going to get values only between 0 and pi. Even if there are other locations down in these quadrants that are going to give me that particular ratio, the only answer I'm ever going to give is the angle that occurs between 0 and pi or 0 and pi. Now, a couple of these, you're not able to actually plug in the asymptotes. And so just keep in mind that for cotangent, it's actually 0 to pi, not including 0 and pi. If it's secant inverse, it's 0 to pi, not including the asymptote at pi/2. If it's cosecant inverse, I know that it's everything other than the asymptote that occurs at 0. If we're looking at tangent inverse, I know that a possible output would be everything other than the asymptotes that occur at -pi/2 and at pi/2. And so let's take a look at a couple examples, because if this seemed a bit confusing, it'll be relatively straightforward when you look at an example. Well, if we're trying to find the corresponding angle that gives me a tangent value of 1, then that's what arctangent of 1 means. Another way to rewrite this would be to solve for theta, where tangent theta equals 1. Now keep in mind that the tangent is positive in the first quadrant and in the third quadrant. So I'm trying to figure out which angle I should give. Should I give the pi over 4 angle that's going to give me a tangent value of 1, or should I give the 5 pi over 4 angle? But this all goes back to the fact that my answer needs to be somewhere between negative pi over 2 and pi over 2. And so I know that it has to be somewhere in this range from negative pi over 2 to pi over 2. Therefore, my answer must be theta equals pi over 4. If we take a look at the next one, notice that the notation is different. Here I use the symbol for secant inverse. Here I use the symbol arc tangent. They mean the same thing. And so in this case right here, we're just saying that secant of theta is equal to 2. Now maybe you've forgotten what that is, but we could also recognize that that implies that cosine of theta is the reciprocal. So either way you choose to do this is fine, but we should realize that cosine of theta equaling 1/2 is going to be either in the first quadrant or in the fourth quadrant, because these are the two locations where cosine theta equals 1/2. One of them being at pi over 3, one of them being at 5 pi over 3. And we know this from our unit circle where cosine theta is 1/2, where x is positive, this is the x-axis, x is positive on the right side of the y-axis. Well, notice how both of these are between negative pi over 2 and pi over 2. So which one do I give? Well, we have to remember that the range for secant and cosine inverse is supposed to be from 0 to pi, not from negative pi over 2 to pi over 2. So I know my answer that I give should be somewhere between 0 and pi, and that means the only possible answer, just like this was at pi over 4, this one must be at pi over 3. So theta equals pi over 3. So now let's go ahead and take a look at the last one. So in order for sine inverse of negative root 3 over 2 to equal an angle, that means that sine of some angle would have to be negative root 3 over 2. Well, the first thing to recognize here is that sine is negative down in the second and third third and fourth quadrants rather. So sine is going to be negative root 3 over 2 down here or down here. And we're not sure which one, but I do know that sine is negative root 3 over 2 at the angles of pi over 3. So the third quadrant pi over 3 angle is 4 pi over 3. The fourth quadrant pi over 3 angle is 5 pi over 3. So now we've got to realize that since we're looking at the values of sine inverse, I know that my angle is supposed to be between negative pi over 2 and pi over 2. So that means it's got to be somewhere between negative pi over 2 and pi over 2. Somewhere in this range right here. Well, you could see that that automatically means that 4 pi over 3 can't be the answer. So you may say that the answer must be 5 pi over 3. But notice that that can't actually be the answer, because 5 pi over 3 starts at the angle of 0 and rotates counterclockwise until it gets to here. That's not an angle between negative pi over 2 and pi over 2. So we need to find a coterminal angle that is between negative pi over 2 and pi over 2. So you either do this algebraically by subtracting 2 pi in order to get me an angle that's going to be in the right range, or simply realize that it's the angle that starts at 0 and goes downwards, which means that the actual answer for sine inverse of negative root 3 over 2 is not 5 pi over 3. The answer is negative pi over 3. And so this is how we find our inverse trigonometric values. Okay, just keep in mind the ranges for each of the 6 inverse trig functions. So here's a quick little reference guide to help us remember what the values need to be. So if we're looking at y equals sine inverse of x, we should realize that our interval needs to be between negative pi over 2 and pi over 2. But notice that there's a few other functions that have to have that same range. Notice here from negative pi over 2 to pi over 2. But notice how this one here doesn't have the endpoints included. The reason they're not included is because those are going to be asymptotes for tangent. Likewise, if we take a look at cosecant inverse, we're going to see that those values also technically go from negative pi over 2 to pi over 2, except 0 is not included right in the middle of that interval, simply because of the fact that that's going to be an asymptote. But now if you take a look at cosine inverse and its reciprocal, secant inverse, then we know that those are going to have intervals from 0 to pi. Cosine is continuous, so everywhere from 0 to pi. While here, it's also going to be 0 to pi, except that it's going to be not including pi over 2, because that would be an asymptote. And likewise, just at the same place that secant has asymptotes, cotangent has asymptotes at 0 and pi. And so we should realize based on this that that means that my quadrants that I'm dealing with are first and fourth if we're from negative pi over 2 to pi over 2. But if we are going from negative, or if we're going from 0 to pi, then I need to make sure that we're somewhere in the first two quadrants. So now let's take a look at this problem. We're expected to find sine of tangent inverse of 3 over 2. So we first of all want to start to interpret what each of these things mean. So first of all, 3 over 2 is describing a ratio on some triangle. And I should also recognize that tangent inverse of 3 over 2 is representing an angle called theta. So what we're really being asked to find is sine of theta. We're being asked to find sine of the angle theta, which means that my answer will become a ratio. So I know by the time I'm done, my answer is a ratio because I'm finding sine of an angle. So the best way to handle these is to draw a sketch. Okay, so if I were to draw this diagram here, I should first of all realize that the angle we're referring to is either going to be, because this is tangent inverse, I know that the angle has to be somewhere between negative pi over 2 and pi over 2. So because the ratio is positive, I know that the angle that I draw will have to be somewhere in the first quadrant. This is my angle, but more specifically, that angle is tangent inverse of 3/2. And so now I just want to draw my triangle here. Okay. So if I draw my triangle, I'm just going to drop my opposite side down to the x-axis, forming a right triangle. And now since I see that the ratio is 3 over 2 for tangent, that tells me that the opposite side is 3, the adjacent side is 2, and now I'm ready to find the hypotenuse. Now notice, I know I'm going to need the hypotenuse because if I find sine of theta, I know that that's my y value over my r value, or my opposite side over my hypotenuse. So I need to do the Pythagorean theorem here. So let's label that C. And let's realize that 3 squared plus 2 squared is equal to the hypotenuse squared. So 9 plus 4 is 13. And therefore C is the square root of 13. So now I come back up here and realize that if this is the square root of 13, and I'm trying to find sine of the angle referred to as tangent inverse of 3 over 2, then all I'm really doing is recognizing that sine of, or that tangent inverse of 3 over 2 is my angle, and therefore by looking at the angle, my answer becomes opposite over hypotenuse. Or to rationalize the denominator, 3 root 13 over 3, or over 13 rather. So always keep in mind that the value inside of an inverse trig function is a ratio, while the inverse trig function itself represents an angle. Well, let's look at a more challenging problem for our second example here. So keep in mind that arctangent of root 3 describes an angle, and arcsine of 1/3 describes a different angle. So why don't we refer to arctangent of root 3 as A, and arctangent or arcsine of 1/3 as B. And so if we do that, we should realize that what we're trying to evaluate is cosine of a sum. I'm trying to find cosine of the sum between A and B. So I needed a formula that represents cosine of A plus B, which we know from our sum formula is cosine A cosine B minus sine of A sine of B. But if we're going to do this process, we're going to need to know what arctangent of root 3 and arcsine of 1/3 are. So notice that both of these are going to have ranges of negative pi over 2 to pi over 2. So if this is negative pi over 2 to pi over 2, then I know my angle has to be somewhere in this range. And so if we were to draw arctangent of root 3 being a positive answer, that would mean that I have some angle right here, which I'll refer to as angle A. And so if I drop my triangle, I could see since arctangent of since I'm dealing with arctangent of root 3, that also means that tangent of theta is equal to root 3, or in other words, root 3 over 1. So that would mean that my opposite side is root 3, my adjacent side is 1, and I could use the Pythagorean Theorem to find my last side. Now notice, this is a special triangle. This is a 30, 60, 90 triangle because I recognize the special sides of this triangle, which means that my missing side, or my hypotenuse, is 2. Okay, well now notice what I'm able to find. I'm able to find cosine of A, and I'm able to find sine of A, because I'm given the triangle, including the angle A. So cosine of A is adjacent over hypotenuse. Sine of A is opposite over hypotenuse. So we now know what sine of A and cosine of A are. But now let's find arcsine of 1/3. Now notice that arcsine of 1/3, since we're dealing with arcsine, is also going to be somewhere between negative pi over 2 and pi over 2. So since this is saying that sine of theta, or in other words, I guess I should say sine of angle B, is equal to 1/3, just like I probably up here should have made this angle A. So I'm now saying sine of B is 1/3, so that must mean that I'm in the first quadrant again. So there's my angle, which means that if I were to draw this as my angle B, which is arcsine of 1/3, then I could drop my triangle and fill in the missing sides. So I know that this represents the opposite side over the hypotenuse. And so that means that this side is 1 and this side is 3. And now I actually have to do some work to find my find my missing side. So let's just call this side, say x. And we know that x squared plus 1 squared is equal to 3 squared. Subtract 1 from 9 to get x squared equals 8. And therefore x is equal to plus or minus the square root of 8, or 2 root 2. Now notice, since we're in the first quadrant, this must be positive 2 root 2. And we're now ready to plug in our cosine of B and our sine of B. So now that we have our triangle involving sine and cosine, I know that cosine is adjacent over hypotenuse, while sine of B is opposite over hypotenuse. But notice we already knew that because that's how we created our triangle in the first place. We knew what sine of B was. And now the last step is to subtract. So when we subtract, we're going to get a value of 2 root 2 minus root 3 all over 6. And this is the exact value of something that seemed relatively complicated simply because I was dealing with inverse trigonometric functions inside of an expression. But when you realize that inverse trig functions are nothing more than angles here, I can draw a triangle in order to represent those angles and fill in the missing sides.